Okay, so today we're starting on 7:15. I know that I need to put up solutions for these three problems, and I will try to get that done before I leave school today. So we last time went over how we actually run or do a significance test for a proportion. So we have to state our hypotheses, check our conditions, find the p-value, make a conclusion. It's a big old long process. So today we're doing that same process for tests about a mean. So everything today will be mu and x bar. Now, hopefully one of the things that we remember from confidence intervals is that to work with a mean, it's different than working with a proportion. So that's where we start today. Confidence intervals and significance tests for a population proportion P are based on z values from the standard normal distribution. So for our last lesson, we used the purple table. Inference about a mean, mu, inference about a mean, mu, uses a t distribution with n minus 1 degrees of freedom. So the biggest difference today is going to be that we do a t-test instead of a z-test. And unfortunately, once we start t-testing, the process becomes a little bit more lengthy. So we use t except in the really rare case when we actually know sigma. And that's very rare. And this goes back to that idea that the reason that we have to use the t distribution in the first place is because we don't know true sigma. So we're going to run through what conditions we're required to check by looking at this example about batteries. Now, the conditions that we check for a test are exactly the same as the conditions we check for a confidence interval. So hopefully that makes this a little easier to manage. So in an earlier example, a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use. So they take an SRS of 15 new batteries and find a sample average of 33.9 and a sample standard deviation of 9.8. Is this sample enough to give convincing evidence that the new batteries last longer? So to find out, we're going to perform a test of HO, which is that the batteries last for at least as long as we're used to, so 30 hours. The alternative that we are checking is that mu is really greater than 30 hours. Because we want to know, do these batteries last longer? One thing to note that's really important is that the numbers in your hypotheses are the same. So on this previous problem where you have to correct the error, one of the biggest issues is that these should both be 0.75. Whatever your hypotheses are, those numbers both need to be the same. So to check our conditions, this is where we start considering the sample. Number one is that we need randomness. So number one, we're checking for randomness. That makes it so that we can make inference about the population. So if our sample's not random, our test isn't valid. Another condition that we need to check is the 10% condition. And I'm hoping that we're feeling pretty comfortable with this guy by now. We just need to verify that we're sampling less than or equal to 1/10 of the population. We don't want to sample more than 1/10 of the population. And then lastly, we have the normal or large counts condition. So normal / large counts. And it's this condition that sometimes causes us to have to do quite a bit of work. So just to make sure that we talk about this a lot, when we check this condition, we're either checking that the population is normal, or we're checking that our sample size is greater than or equal to 30. Because in this case, the CLT applies. So they're two different things that we can use to check the same condition. As in the previous chapter, the normal or large counts, there should be a counts there, or no, yeah, large counts. The normal or large counts condition for means is that the population distribution is normal or sample size is large. So we basically just wrote those same things down. The issue is we often don't know if the population is normal. So this is the biggest issue here. We often don't know if our population is normal. So if the sample size is large, we can run the test because of CLT. If the sample size is small, then we need the sample, we need the data so that we can graph it and check to see if it's reasonable to assume that it's normal. And as a reminder, we're looking for skewness and outliers. If there's strong skewness and outliers, we can't use a t-test. Okay, so we're going to check the conditions for our AAA batteries. First one is randomness, and you can check these in any order that you prefer. So an SRS of N equals 15 new batteries was taken. And you can say AAA batteries if you prefer to be really specific. %% condition is up next, so we're going to do N, capital N, our population, is all new AAA batteries. So it's definitely reasonable to assume that 15 is less than 1/10 of that. They probably produced way more than 150 batteries. And then last is checking our large counts or normal condition. In this case, unfortunately, N is equal to 15, which is less than 30. So what we are looking for is whether the population is normal. So to do that, we have to have the data or a graph of the sample data. So the textbook provides for us the dot plot. I don't know why they give us the dot plot because I would never use this. This does not help me see the shape and if there are outliers. That's me personally. I love to use the box plot. He has skew, he is right skewed, but it's not strong, and there are not outliers because remember on a box plot, your outliers will show up. Then the one other thing that we have discussed is your normal probability plot. Your normal probability plot. And what you look for on this plot is that it's fairly linear, or that it has a linear form. I often will not use this as my graph, and if I do, I still do the box plot. And the reason why is because I find it hard to label the axes on a NPP. Like, I'm not even really sure what they mean. So I'll do the box plot and label everything correctly, and then just use the NPP to support my decision. Sometimes I graph it, sometimes I don't. As long as you have one, you're good. You can get full credit. So n is equal to 15, which is less than 30, but the box plot below shows no outliers. I don't know why that word 2 is there. No outliers. Or strong skew. Normally, I can say the box plot is fairly symmetric, but in this case, it's not. It's obvious that this has skew, so the reason that it's okay is because it's not strong skew. So I'm pointing out that it doesn't have the things that we worry about. And the NPP is fairly linear. Remember, you can use one or the other or both. One is what is required. So based off of that, it's reasonable to assume the data came from a normal distribution, and we can use T procedures. So the whole point of checking large counts or normal population is so that we can verify we are allowed to use a T distribution. So I just want to reiterate one more time that this is exactly the same process that you use for checking confidence intervals. So that is part 1 of this lesson.